Our universe is constantly expanding, stretching the fabric of spacetime in all directions. This expansion makes it incredibly difficult to define where the universe begins or ends. There is no clear edge to the cosmos, making its true size a mystery beyond human comprehension. At the heart of this expansion is dark energy, a mysterious and invisible force. Dark energy is believed to be the reason the universe's expansion is accelerating over time. Instead of slowing down due to gravity, galaxies are actually moving apart, faster and faster. Scientists track this cosmic motion using a method called red shift measurement. The greater the red shift, the faster a galaxy is moving away from us, which confirms the expansion. To improve our view, scientists rely on powerful telescopes, including the James Webb Space Telescope. This telescope provides unprecedented clarity, especially in the infrared spectrum. Unlike its predecessor, the Hubble Space Telescope, Webb can see through cosmic dust. This allows it to reveal hidden structures that were previously invisible to astronomers. Before Webb, Hubble gave us most of our deep space images and taught us much about the universe. However, Hubble's limited infrared capabilities left significant gaps in our understanding. The James Webb Telescope, positioned at range 2, avoids Earth's interference completely. It captures clearer images by remaining stable in this gravitational sweet spot far from Earth. Webb has already discovered galaxies that formed just 300 million years after the Big Bang. These ancient galaxies are surprising scientists and challenging models of cosmic evolution. Renowned astrophysicists like Brian Cox and Neil deGrasse Tyson often emphasize how vast the universe truly is. Cox famously compares the observable universe to a grain of sand on an endless beach. Currently, the observable universe spans about 93 billion light-years in diameter. Yet, this is only the portion we can see, limited by the speed of light and the age of the universe. Beyond this observable bubble lies the unobservable universe, which may be infinite. We may never be able to see or reach this part of the cosmos, making it forever beyond our reach. Within the observable portion, there are an estimated 2 trillion galaxies. Each galaxy holds billions or even trillions of stars, forming vast cosmic cities. These numbers come from deep field surveys, including iconic images taken by Hubble. In 1995, Hubble captured a small patch of the sky, revealing thousands of galaxies in a single image. Later surveys showed that galaxies form a cosmic web, not a random spread. This web is made up of filaments, voids, and clusters, all shaped by gravitational forces. Even though our solar system feels massive, it is tiny compared to the Milky Way. To put this in perspective, driving at 70 miles per hour, it would take 15 days to circle Earth's equator. Yet it would take 5 months to reach the Moon and 63 years to reach Mars at its closest. When compared to interstellar distances, these seem like short trips. Voyager 1, launched in 1977, has been traveling for decades. In 2012, it exited the solar system, but still hasn't reached the Orb cloud, a distant shell of icy debris. This cloud surrounds our solar system and marks the edge of its gravitational influence. Even traveling at light speed, which is 670 million miles per hour, distances in space remain mind-boggling. Light from the Sun takes 8 minutes to reach Earth, but from Alpha Centauri, it takes 4.3 years. At Voyager's speed, it would take 70,000 years to reach Alpha Centauri. This shows how impractical interstellar travel is with our current technology. Even our closest exoplanet, Proxima Centauri b, is still out of reach. Our Milky Way galaxy contains about 300 billion stars, many with their own planetary systems. The galaxy itself spans 100,000 light-years, and Earth is located about 26,000 light-years from the center. At its center lies Sagittarius, a supermassive black hole with 4 million times the mass of the Sun. Stars near it orbit at incredible speeds, pulled by its immense gravitational force. Our solar system lies in the Orion Arm, one of the galaxy's spiral arms. It completes one orbit around the galaxy every 230 million years, a journey we barely notice. Beyond the Milky Way, we are part of the Local Group, a collection of 54 Galaxies. The Andromeda Galaxy, our nearest large neighbor, lies 2.5 million light-years away. It is moving toward us at 68 meters per second and is expected to collide with the Milky Way in about 4.5 billion years. Such galactic collisions are common, but stars rarely collide due to the vast space between them. This collision will result in a new elliptical galaxy, a beautiful reshaping of cosmic structure. These galaxies group further into clusters and superclusters. The Virgo supercluster, for example, includes 1,500 galaxies. It is a part of the larger Lockyer supercluster, which spans 520 million light-years. Lockyer means immense heaven in Hawaiian, a fitting name for such a massive structure. Superclusters are connected by filaments of dark matter and gas, forming the cosmic web. Between these filaments lie voids, empty regions, spanning hundreds of millions of light-years. In total, the observable universe contains about 10 million superclusters. Yet all of this makes up less than 5% of the universe's total content. The rest is composed of dark matter and dark energy, both invisible and mysterious. Dark matter makes up 27%, holding galaxies together with its gravitational pull. Many scientists believe the universe could expand forever, becoming colder and darker. This is called the Big Freeze, where stars die, galaxies fade, and energy runs out. Others suggest a Big Rip, where expansion tears apart atoms and space itself. There's also the Big Crunch, where gravity might reverse the expansion, collapsing the universe. We don't yet know which of these will happen. It all depends on the nature of dark energy. This is one of the greatest questions in modern cosmology, still without a clear answer. To study these ideas, scientists simulate the universe using supercomputers. These simulations model how galaxies form and move over billions of years. By comparing them with actual observations, we can test theories of cosmic evolution. One such simulation is the illustrates the universe in 3D. It models 13 billion years of evolution and includes stars, gas, dark matter, and black holes. These simulations show that structure in the universe follows predictable patterns. They confirm that gravity, dark matter, and dark energy guide the motion of galaxies and clusters. The cosmic microwave background, CMB, is another key to understanding the universe's birth. It is the faint glow of radiation left over from the Big Bang about 13.8 billion years ago. This light was first detected in 1965 by Pensars and Wilson using a radio antenna. Today, satellites like Planck have mapped the CMB in fine detail. These maps showed tiny temperature fluctuations which are the seeds of all structure we see today. These small differences grew into galaxies, stars, and planets over billions of years. The uniformity of the CMB supports the idea that the universe began in a hot, dense state. The CMB also proves that space is flat, not curved like a sphere or saddle. This flatness helps scientists calculate the total size and density of the universe. Measurements show that the universe is expanding uniformly on large scales. However, gravity causes local clumping which forms galaxies, stars, and planets. One great mystery is why the universe has such perfect balance. A small change in density would have led to collapse or runaway expansion. This delicate tuning makes scientists wonder if we live in a fine-tuned universe. Some think this suggests the existence of a multiverse, many universes with different properties. In this view, our universe is just one bubble in a cosmic foam, where other bubbles might exist. These universes may have different physics, making life impossible in most of them. If true, the multiverse could explain why our universe seems so perfectly suited for life. There is also the possibility that the universe is cyclic, endlessly expanding and collapsing. This idea suggests that time has no true beginning or end, just a series of cosmic cycles. Meanwhile, our understanding of time itself remains incomplete. Einstein's theory of relativity shows that time is linked with space forming spacetime. This fabric is bent by mass and energy, causing time to slow near massive objects. We have tested this with atomic clocks placed on airplanes and satellites. They tick differently, depending on speed and gravity, proving that time is relative. In black holes, time can slow to a stop, a place where our laws of physics break down. The edge of a black hole, called the event horizon, is the point of no return. Inside, matter collapses to a point of infinite density called a singularity. We don't know what happens at a singularity because we lack a theory of quantum gravity. This is the missing link between Einstein's relativity and quantum mechanics. Physicists like Stephen Hawking have tried to unite these theories to explain the universe's origin. Hawking proposed that the universe may have no boundary in spacetime. According to his theory, the universe could have emerged from a quantum fluctuation. If true, this means the universe began without a clear cause or moment of creation. Despite all our progress, we still understand only a fraction of the cosmos. We don't know what dark matter is made of or what dark energy actually is. We don't know if life exists elsewhere or if humanity is alone in this vast space. We continue to search, with projects like SETI, listening for signals from intelligent life. The Drake equation attempts to estimate how many civilizations might exist in our galaxy. It includes factors like star formation rate, planet habitability, and technological lifespan. Even with conservative numbers, it's likely that life exists beyond Earth. In recent years, telescopes like Kepler and TESS have discovered thousands of exoplanets. Many of these lie in the habitable zone where liquid water could exist. We've also found Earth-like planets around stars just a few light years away. Still, we've yet to detect biosignatures, evidence of life on these worlds. Future telescopes like the LUVI and HABEX missions may change that. They aim to image exoplanets directly and search their atmospheres for oxygen, methane, and water. These clues may finally answer the age-old question, are we alone? Back on Earth, humans have only begun to explore the universe. Our current space missions barely scratch the surface of the cosmic frontier, but each discovery changes our place in the universe, showing how much there is to learn. From the tiniest quantum particles to the largest galaxy clusters, everything is interconnected. We are made of star stuff. As Carl Sagan said, atoms forged in dying stars. We live on a small planet orbiting an average star in a spiral galaxy among billions more. And yet, through science, we can understand the laws that govern everything. Subscribe to our channel and thanks for watching.